In this video, we discuss Stokes theorem. So, a short statement of Stokes theorem is integral or f bar of f bar over a curve C is the integral of the curl over a certain surface S. So let's just try to understand this theorem with the help of a diagram. Let me draw the surface. So I have a certain surface in the three-dimensional space, that's S. The bounding curve is C. It is given a certain orientation. Will not bother about it too much as of now. The left hand side therefore is something which is happening on the curve C. So it is the line integral over this curve C. That is the left hand side. What is the right hand side? The right hand side, so let us fix a point on the surface. This point, let us say, is XYZ. Evaluate the curl of the vector field at this particular point. So that's the quantity del cross F bar. That's going to be a vector. Take that vector. So let us say that the vector, this is the vector del cross F bar. You're supposed to dot it with another vector. What is this? Let us look at a small patch, an infinite small patch at this particular point. This patch has a certain area. The magnitude of the area is ds, and it has a direction. The direction is that of the normal to the surface. Let us say this is the direction of the normal to the surface, n cap. So ds n cap is our ds bar. So one is evaluating del cross F bar at a particular point and looking at its projection in the direction of n cap. So you'll get some scalar quantity, and you are adding up all such scalar quantities over the surface. You get the right hand side. So what is Stokes theorem saying? The Stokes theorem is saying that a certain phenomena happening on the surface can be captured on the boundary. Okay? And vice versa. So Stokes theorem is a transformation equation. It transforms a line integral into a surface integral and vice versa. Green's lemma is actually a special case of Stokes theorem. Let us see that. Well, so the notation is the following, that we will be writing f bar to be f1i plus f2j plus f3k. R bar will stand for the radius vector xi plus yj plus zk, and therefore dr bar will be dxi plus dyj plus dzk. Okay. So we want to reduce this to the two-dimensional situation, and so if I have to draw the diagram, so the surface S is now in the plane, in the xy plane. So this is my curve C, and the points enclosed by C is the surface S. All right. What is ds bar? So a small area element will be dx dy, that's the magnitude, and the direction that you wish to give is the one along the positive z axis. So the direction is n cap. This is our ds bar. Okay. So integral f bar dot dr bar becomes integral of okay, so del cross f bar, let's evaluate that. K cap, that's what is happening. Okay, and del cross f bar, I can evaluate it this way. F1, F2, F3. So now in this case, the vector field f bar is F1i plus F2j, where F1, F2 are functions of just x and y. But here F1, F2, F3 are functions of x, y, and z. All right. So if I have to come from this situation to this situation, I can put z equal to 0, and also I can put f3 equal to 0. Okay. So there will be no z in f1 and f2, and f3 is 0. I wish to evaluate this. This is equal to I. The partial derivative of 0 with respect to 0 is 0 minus the partial derivative of f2. There is no z here. 0 plus j. So the partial derivative of f1 with respect to z, there is no z here, minus the partial derivative of 0 with respect to x. So that's again 0 plus k times dabba f2 by dabba x minus dabba f1 by dabba y. All right. So I take this and put it in this. So integral f bar dot dr bar is equal to, so dabba f2 by dabba x minus dabba f1 by dabba y. Okay, that's the curl with direction k, and dotted with k dx dy. Okay, so this is integral dabba f2 all this over s all this over c f2 by dabba x minus dabba f1 by dabba y dx dy, which is precisely the statement of Green's lemma. Okay. I'll make one remark and stop. Now, suppose we have this situation. We have a surface and we have this bounding curve C, surface S1. Suppose there's one more surface, S2, with the same bounding curve. Okay. Then from Stokes theorem, it becomes clear that dabba, okay, the curl del cross f bar dot ds bar over the surface S1 is equal to the curl dot ds bar over the surface S1, S2. Now, this is not difficult because if you apply Stokes theorem to the left hand side, okay, so this is integral over C f bar dot dr bar, and if you apply Stokes theorem to this, what you have is this. All right, so these two have to be the same. This is actually very useful in working out problems. Right, so one should try to take advantage of, you can call this as a corollary to Stokes theorem. So I stop here in this video.